Good evening. A light smattering of applause. Thanks for having me here tonight. It's a great honor and a great pleasure to come and talk to you about Formula One. Formula One is arguably the greatest racing spectacle on earth. There's hundreds of, well, there's a Formula One fan. I knew there was going to be one. 500 million fans who tune in to the event every single time we put on a race. It really is arguably the greatest racing spectacle. But we at Formula One, we have a mission. We want to make it more engaging, more intriguing, just a better overall product, something that entertains more. And there's a key strategic moment coming up for us, an opportunity in 2021, where we're going to make seismic shifts and changes in the technical regulations, in the sporting regulations, in the sport overall. And when we engaged our fan base and we asked them, what do you want? The biggest thing that everybody wants is more wheel-to-wheel racing. They want to see the cars, you know, inches from each other and racing, like all of them great iconic moments that you've seen. And the enabler to do that, believe it or not, is aerodynamics. So let's talk about the aerodynamics, and I'm going to take you through that story. So the first part of it is aerodynamics. Why bother? What does it do? The teams work relentlessly to produce downforce. Downforce is what pushes the car into the ground. It's what creates grip. It's what makes the cars such a spectacle going around the corners at such high speed. And then you've got the other part of aerodynamics, which is drag. Drag is the part that slows the car down in a straight line. So as the car goes down the straight, being powered by 1,000 horsepower, the drag's trying to slow it down. So you want to maximize the downforce, but you want to minimize the drag. And if we look at the development rates in Formula One, of downforce in particular, it's huge, it's immense. So the curve that you can see behind me here is fairly representative of a downforce curve. And as the speed increases, the downforce goes up. And it's exactly the opposite of an aeroplane. So when you sit on the tarmac and you go down the runway, as you build up the speed, eventually the wings give the aircraft enough lift and it goes up in the air. Formula One car is exactly the opposite. As the speed goes up, it gets pushed further and further into the ground. And at a certain speed, as you can see here, at around about 100 miles an hour, this is just to give you an example of how much downforce these cars generate. At around about 100 miles an hour, it creates about 1,000 kilos of downforce, which is about the curb weight of the car. So that means that if we turned the racetrack upside down and ran it above 100 miles an hour, it would actually be able to run upside down and stick to the ceiling. So how do we develop aerodynamics? There's two ways that we develop aerodynamics in Formula One. Large teams of engineers, they work in the wind tunnel and they work in CFD, computational fluid dynamics. The wind tunnel, it's a scale model, around about half the size of the car. It's a very, very accurate representation. We make changes to that scale model. We blow air over it inside the wind tunnel, and we check whether them changes are positive or not. Computational fluid dynamics, instead, is essentially a virtual car in a virtual airspace. And we've been using CFD now for about 20 years. And as we've got more and more sophisticated with CFD, it's given us more and more insight into the flow physics. And what you see behind me here is a really, really interesting slice of the rear axle of a Formula One car. Those two blue dots that you can see towards the center line, they're called the vortex structures. And vortex structures are the aerodynamicist's friend, because they're very, very high energy airflow that go under the diffuser, underneath the floor of the car, and they create suction and pull the car into the ground and create grip. The pink hue that you see around the outside of the car, that's called the aerodynamic wake. And what the aerodynamic wake does is when the free stream, when the air passes over the car, it gets very, very turbulent, it becomes non-laminar, and it creates this wake, which is bad for aerodynamics, wake bad, okay? And when we looked at how we were going to improve Formula One, it was this wake structure that we had to improve. And essentially, this gives us the development, the golden triangle in Formula One, where you go from CFD to wind tunnel, to the track, you test it, and then you go back again. And you keep going round and round this golden triangle. And CFD plays a huge part, plays a very, very key part in the development. And CFD has always been a supercomputer problem. It's always been a HPC problem. The architecture that you can see behind me here, believe it or not, is the first architecture that we used in Formula One. And what we did was we took 20 CAD terminals, and when the designers went home on a night, we used to daisy chain them all together. And we made our first supercomputer, a 20-core supercomputer. Believe it or not, that's exactly what we did. And we used to do the CFD runs. And when they came back in the morning, we'd disassemble them. Today, we use around about 200 cores within the teams, and it's about 2,500 times the computational power that you can see of that architecture there behind me. So let's frame the problem. The problem is this. The car behind, the red car, in our diagram here, when it's 1 second behind, it loses 30% of the downforce, a huge number. Okay? When it's half a second behind, which is the speed that you need to close in and get this wheel-to-wheel racing that we're searching for, it's losing 40%. So we turn to Formula One, we turn to aerodynamics and the CFD in Formula One in order to try and solve this problem. And what we had to do is we had to build a two-car simulation. What you see behind me is the current generation of cars. And when you see the wake effect, when we go into the pressure domain and you see the wake effect of that car behind, you can see how powerful it is and how much it destroys the aerodynamics of the car behind. This is where we lose around about half of the downforce. So what we had to do is we had to set around designing a new generation of car in order to improve the wake effect. And what you see behind me here is the 2021 version. This is what's coming up, okay? And what you're going to get as this animation moves around is a driver's eye view. So right now, you can be sat behind that car, and you can see the wake effect. It's an upwashing wake, and it's going over the car. But we had to completely redesign the car to make that happen. It's a huge HPC problem, a massive HPC problem. And this is where the partnership between Formula One and AWS was so important. Two companies, their DNA in problem solving. Let's just try and frame for a second the size of the HPC problem we've got. If you take a single car CFD run, and you take the most powerful home computer on the market today, if you wanted to do one run with a single car, not the two cars that we're talking about, it would take you around about 14 days, 2 weeks. Even with the team technology of 200 cores, it still takes about 4 days to do that two-car simulation. It's nowhere near, absolutely nowhere near the agility that we need in order to develop a new Formula One, a better Formula One. Okay? Partnering with AWS and their cloud HPC services, EC2, the first iteration for a two-car simulation, we got down to 11.5 hours. We're now at less than half. We're now at less than 8 hours. 8 hours to do a two-car simulation. So it's absolutely incredible what we've been able to do. It gave us the agility to be able to move forward. And I'm going to give you when we were putting this together, this talk together, I'm not American, I don't know whether any of you noticed, but some of the guys who were putting it together, they called these the face melting stats. And I think this really is face melting. This was an email that I received just some weeks ago about where we are now with what we call the Mike model, which is up there, okay? We had 7,300 cores solving 14 cases all at pretty much the same time. 2.7 billion cells within the CFD models to solve. And we did it all in less than 30 hours. It's absolutely incredible what we've been able to do. And what that's done is it's given you this behind me, the 2021 Challenger. This is what we hope is going to change Formula One. And we are hopeful. It's exactly what the fans are asking for. So what are the results? The results are this, okay? At 1 second behind, rather than losing the 30% of downforce, we're now losing 5% of downforce. All right. At half a second behind, 7%. It's huge. It means that the car's being pushed into the ground more. It means we can get this wheel-to-wheel action. Okay? It's exactly what we've been searching for. And we're really, really hopeful that it's going to make a better show. okay? Two great companies, two great partnerships, okay, or a great partnership, Formula One, AWS, the DNA in problem solving. Thanks very much for having me. It's been an absolute pleasure.